Okay, welcome everyone. This is the last colloquium talk of the semester. We're happy to have Anna Puskás from the University of Glasgow, who will speak on p-adic groups beyond the finite dimensional setting. Thank you for giving the talk, Anna.
Well, thank you very much for having me, and thank you everyone for coming. Um, I will try and talk about a topic that is a lot of interest to me, which is the p-adic or reductive, or more generally Kac-Moody groups over a p-adic field. I'll say what I mean more exactly in a moment. So roughly, I'll just give a brief overview of what I'll talk about, and then I will talk about some formulas and some facts about the representation theory of reductive groups that generalize or maybe not to the infinite dimensional setting. So when we view our reductive groups as examples of a Kac-Moody group, that may then also be infinite dimensional. And then I will move on and see what happens in the infinite dimensional setting. I realize that 3.1, what is a Kac-Moody group, makes it look like I will answer that question. I will say some words about it. In general, this topic is fairly large, so I've chosen to give an overview most of the time rather than go into details, but please feel free to ask questions if something is unclear, and then I shall try to answer them. Right. So roughly, I will talk about the following things. So our main object of interest is going to be a group. You should always feel free to think about uh, the special linear group over the p-adic numbers, if you like. Well, of course, this is not infinite dimensional, so we will eventually think of some generalization of this. And this will have some interesting subgroups: the maximal compact, the Iwahori subgroup, a torus, a Borel, a unipotent radical of the Borel. I'll come back to these. And really, the main objects of interest for us will be the corresponding spherical Hecke algebra and Iwahori Hecke algebra. I'll say more about these in a moment too. And the facts that will be interesting to us are things like the structure of the group G. So, for example, its decomposition theorems or the corresponding root datum, the Satake isomorphism of the spherical Hecke algebra, and the Bernstein presentation of the Iwahori Hecke algebra. And some formulas we will encounter is the McDonald's formula for the spherical function related to HK, and the Kassaman-Chaleiko formula for spherical Whittaker functions, I guess closer related to HI, but maybe that's neither here nor there. And at first, this G will be a familiar reductive group, so think of your favorite matrix groups as examples. But then we will replace it by, well, either a loop group of that or more generally a Kac-Moody group. Okay. So this is just a very brief overview. You will hear these words again and again. And so you might ask, what is one's motivation to study such objects? Well, here I will be very vague, partially because, of course, your motivation to study these objects depends a lot on what you are interested in. I mean, so for example, you might be interested in number theory, so studying groups or their representations over number fields, global fields such as Q. You might want to understand, for example, Eisenstein series on GLN-Q. And even, I mean, even GL1Q is very interesting, right? And so, for example, if you want to understand these global objects, you might want to study them adelically and then in turn locally. So for example, you might want to understand the Whittaker Fourier coefficient of an Eisenstein series as local Whittaker functions, so as objects in the local representation theory of these now p-adic groups. And so more generally, if you want to study automorphic forms via smooth and admissible representations of a local group. So these are representations that where a vector has an open stabilizer and an open subgroup has a finite dimensional invariant subspace. you can turn these representations of the group into representations of a Hecke algebra corresponding to the open subspace. And so this is one way in which the representations of, for example, the spherical Hecke algebra or the Iwahori Hecke algebra come up. Of course, you can think about these objects completely locally as well. And in fact, so for example, the Iwahori Hecke algebra was used by Kazhdan and Lustig to define Kazhdan-Lustig polynomials, which were then used to define a representation of the Iwahori Hecke algebra and a canonical basis, both in the algebra and the representations. But these objects are also related to things in geometry. So, for example, the singularity theory of Schubert varieties, and they appear in the decompositions of Verma modules of Lie algebras. But many of these objects, as we'll see, can be defined completely combinatorially. And so there are correspondingly a lot of connections to objects just in pure algebraic combinatorics. So you might encounter a Hecke algebra finite or affine and never have heard of a p-adic group before. And that's a perfectly reasonable way to be. But then through these definitions, you might study these objects in terms of combinatorial devices such as highest weight crystals, or explore connections to Schubert varieties or particle physics through, for example, solvable lattice models. I mean, I'm mentioning a lot of things here, but of course, I mean, to talk about these in detail would take a long time and perhaps more knowledge in some cases that I have. But any of these objects might put you in touch with something like an Iwahori Hecke algebra. So hopefully this will be interesting for that reason. And then, of course, reductive groups appear everywhere in mathematics, but it might be a bit more of a stretch to then be interested in the infinite dimensional setting. But so, for example, one way so-called affine groups come up is as loop groups associated to finite dimensional groups. And these were used, for example, to explain phenomena in soliton equations. So some Backlund transfers in the work of Turing and Uhlenbeck. But also, for example, if you take, maybe an affine Lie algebra, then its characters of a certain level are invariant under an SL2Z action. So if you're interested in representations of SL2Z, which you might be if you're a number theorist, then this is a topic in which they come up. Okay, well, let me say some slightly more concrete things. So first, I have to introduce some notation. So in the finite dimensional setting, I talk about p-adic groups, but really what I mean is groups over a non-Archimedean local field. So think of your favorite example. For example, you may think of the p-adic numbers or Laurent polynomials over a finite field. And in this non-Archimedean local field, we will have a ring of integers. For example, the p-adic integers, or sorry, I already made a mistake. Or Laurent polynomial. I should have said Laurent polynomials then. There we go. Or sort of power series in T then. And then we can think of a reductive group. So again, this can be almost anything, but let's think of G as the the special linear group over the p-adic numbers. And such a group is, importantly, it's locally compact because the field a field is sort of has some topological structure. So G has the structure of a topological group, which is locally compact, and therefore there's a Haar measure on it. And there's an associated root datum, which explains the structure of G. Well, for SLR, this will be of type AR minus 1. And then there's a maximal torus, a co-weight lattice, and a Weil group associated to it. These will play a role in our story. So for example, in SLR-QP, the maximal torus, a maximal torus we may choose, it consists of the diagonal matrices. This is isomorphic to QP cross to the R minus 1. It's a split torus. The co-weight lattice of co-characters into this maximal torus is a lattice. Well, here it's isomorphic to Z to the R minus 1. Whoops, R minus 1. And there's a Weil group, the normalizer of the torus mod the torus. In this example, it's the familiar symmetric group on R letters. Okay. And importantly, there's a maximal compact subgroup in G. You can show that this is G of O. That's not completely trivial, but you can sort of work it out by looking at what subgroups of G fix a lattice. And so, for example, for us, this will be SLR ZP. I just mentioned that when we move to the finite dimensional setting, this maximal compact subgroup, well, the topology is all much worse. So this maximal compact subgroup doesn't quite make sense the same way anymore. And in fact, what to replace K by becomes a bit of an issue. Okay, and then in K, we have the Iwahori subgroup. Well, the integers of f can be modded out by a maximal ideal to produce a finite field of Q elements. Q will pop up in our formulas fairly frequently. And if we apply this, if we extend this projection to all of K, we get G, the group over a finite field, and we can pull back a Borel subgroup, so let's say the upper triangular matrices, and get the Iwahori subgroup. So if you've never seen this before, don't worry too much about it. It is an open compact subgroup of G. Okay, and then the spherical Hecke algebra is going to be the convolution algebra of compactly supported k bi-invariant functions on our group. So these are functions from the group to, let's say, the complex numbers that are invariant when I multiply the argument by elements of the compact subgroup. Okay, I mentioned that I put C here, but it's handy to have something that's algebraically closed and zero characteristic, but it doesn't make much of a difference beyond that. So the special properties of C are not really used in the theory. Okay, and again, so the multiplication on this algebra is by convolution with respect to the Haar measure. So for two functions on G that are both k bi-invariant, I can take their convolution by taking an integral over G, such as this one. And again, this requires a Haar measure, something that we will have to do without in the infinite dimensional setting. Okay, and here are just some facts about the group. So first of all, we have a Cartan decomposition. G can be written as a disjoint union of K double cosets. And well, it turns out that the double cosets are exactly indexed by the dominant part of the co-weight lattice. So this is the dominant. This is by dominant co-weights. It's well, it's sort of a Weil group fundamental domain within the co-weight lattice. Okay, and we can show that in fact spherical Hecke algebra is isomorphic to the symmetric portion of the group algebra of the coweight lattice. This is the Satake isomorphism. So for SL or QP, these would be, we can think of these as an algebra of symmetric polynomials. Okay. And now, I mean, we will be somewhat concerned with the bases of these algebras that we talk about. So, I mean, the basis, a natural basis of this spherical Hecke algebra of k biinvariant functions is given by characteristic functions, characteristic functions of double cosets. So functions of the form 1 chi pi to the lambda k that are 1 on exactly one of these double cosets in G and 0 everywhere else. And well, we might ask, what does this function map to when I apply the Satake isomorphism? I'm just for now going to call this element of C lambda check W, this symmetric polynomial, a spherical function. And later this is going to appear in McDonald's formula. So when I talk about McDonald's formula for the spherical function, this is what I mean. I mean a basis element of the spherical Hecke algebra, the image of the natural basis by the Satake isomorphism. Are there any questions so far? If no, then let me go on to the Iwahori Hecke algebra. So similarly to the spherical Hecke algebra, I also give the Iwahori Hecke algebra as an algebra of biinvariant functions on G, now biinvariant with respect to the Iwahori subgroup. So remember, E was this Iwahori subgroup. So it is a subgroup of K. So this is a larger algebra, and in fact, it will turn out not to be commutative. So again, the multiplication is defined with respect to via convolution with respect to a Haar measure. I mean, when we define these convolution integrals, we use a Haar measure that is normalized. Here we would use one that gives the Iwahori subgroup measure 1, whereas previously in the spherical Hecke algebra we would normalize so that the maximal compact has measure 1. The ratio of those two can be given. Okay, and again the basis is given by characteristic functions of double cosets. And now the question is what is the correct thing to index these double cosets with? And it turns out that is a semi-direct product of the Weil group and the coweight lattice, which is the affine Weil group. This follows from the Cartan decomposition and the Bruja decomposition of G. Okay, but what we get as a result is a deformation of the group algebra of this affine Weil group. So again, it's something that we could have defined completely combinatorially, and we will look at the presentation in a moment. So this is an extended affine Hecke algebra. So I remarked that here the affine Weil group or extended affine Weil group that I can define as a as a semi-direct product of the finite while group and the co-weight lattice is, well, almost a Coxeter group. So if W is generated by R simple reflections, and then W tilde is generated by one extra simple reflection, and well, maybe another maybe a length 0 element. But if my group G is simply connected, then I don't have to worry about this. This is just a Coxeter group itself. Okay, and well, the Ihori-Hecke algebra has this basis of TW consisting of these indicator functions of double cosets, but based on the structure of W tilde as a Coxeter group, I can give this a so-called Iwahori-Matsumoto presentation. So it is generated by elements Ts, where S is a simple reflection in the while group, again, one of R plus 1. And these have some relations. There's a quadratic relation. Ts squared is q minus 1 times Ts plus q. Again, remember here q was the order of the residue field. And then the Ts satisfy braid relations. Now, these two relations give a presentation of the algebra where W tilde is Coxeter, and even if it's not, we can replace the braid relations by this other relation that TUV is TU times TV if and only if U and V give a length additive product in terms of the Bruchau order, the sort of Bruchau length in the while group. So here I have this length function from the affine while group to non-negative integers related to reduced decompositions. Okay, but there's also another presentation of the Ihori-Hecke algebra corresponding to the fact that this affine while group has a large commutative subalgebra, this lambda check co-weight lattice. There's the Bernstein presentation which manifests this the group algebra of it as a large commutative subalgebra. The Ihori-Hecke algebra is the tensor product of a finite Hecke algebra generated by the simple reflections in the finite while group. Sorry, generated by the Ti corresponding to the simple reflections in the finite while group, tensor C lambda check, and the relationship of these two is governed by the Bernstein relation. Okay. Any questions? Please stop me. Okay. And now, again, I'll list a couple of formulas. And of course, I mean, this is all happening fairly fast. So I have to say that I realize I haven't introduced these formulas quite properly for lack of time. But the takeaway should be, especially if you haven't seen these formulas before, to just show their rough shape and their relationship to one another and to the algebras and the objects that I've mentioned above. So, you know, if you can't quite absorb all the details of these formulas, don't worry about it. We probably won't need it. Okay. So the first formula is Macdonald's formula for the spherical function. Again, remember the spherical Hecke algebra is this algebra of k bi-invariant functions on G. It is via the Satek isomorphism, isomorphic to an algebra of symmetric polynomials on the co-weight lattice. And the image of the natural basis is what we call the spherical function. So Macdonald gave a formula for this, and it's a beast. So this is given in terms of a while symmetrizer, so a sum over the while group. So this is a while symmetrizer. It can be thought of as the output of an operator acting on C lambda check. And I'm just going to have to write it down. It involves a product over positive roots. That's what this phi plus is. 1 minus q inverse e to the minus alpha over 1 minus e to the minus alpha check times e to the w lambda. We're thinking of this e to the w lambda as a basis element of c lambda check. And then I have to insert some constant here. Scale rho is the wild vector, half the sum of positive roots. And here on the bottom, I have the Poincare polynomial of the Weil group, or rather a portion of the Weil group. So this is something like a Poincare polynomial. And I just mentioned that if you're familiar with this topic, you might recognize the argument that W acts on here, this coefficient, as a Gindikin-Karpelevich product. Oops. Which is the value of some intertwiner on a spherical function, but let's not talk too much about that now. Okay, so this is a Weil symmetrizer. It is an element of, it is a symmetric polynomial. And the other sort of little bit similar looking formula I wanted to mention is the Kassaman-Shalaka formula for a spherical Whittaker function. So again, this is a spherical Whittaker function is a function on G that is right invariant under the maximal compact, left equivariant under the unipotent radical of a Borel and a character, and it's an eigenfunction of the spherical Hecke algebra. And well, it's a fact that because of the Iwasawa decomposition of G, it suffices to give its values on values of the form pi to the lambda. So this is an element of the torus of G corresponding to an element of the co-character lattice. So it's sort of the image of a co-character. And on an element pi to the lambda, a spherical Whittaker function is zero if the element is not dominant, and if it is dominant, then it is given again by something that is sort of almost symmetric by the Weil group. Let me just write it down and then we can talk about it. So it's given as a multiple of a character of the Langlands dual of G. With highest weight lambda. Okay. So again, the proof of all this is beyond the scope of this talk, but I want to say that I want to make a few comments about these formulas. So one of them is that, which may not be immediately obvious, but both of the formulas are really given as Weil symmetrizers here. Well, why? This character of the Langlands dual can be expressed using the Weil character formula as a similar sum over the Weil group. So really, in both cases, we have a sum over the Weil group, with some operator associated to the while group acting on C lambda check, and then we have some sort of similar expressions appearing and some normalization in terms of Q that maybe we don't have to worry too much about. So both formulas are given in terms of these while symmetrizers. So again, I have some element, some sum over the while group, and then some operator indexed belonging to W acting on some e to the lambda. This is the cartoon plus some normalization ahead of it. Okay. They also have expressions as Hecke symmetrizers. So, well, I mean, the way I will write it will look kind of similar, but instead of acting on acting on e to the lambda check directly with an element of the while group, as we've seen above, we can act on them by an element of an algebra. Some sort of symmetrizing, and then again have some kind of normalizer. So these TW here, these are some version of a Hecke algebra basis. So remember, this is how we denoted the double coset basis of the Iwahori-Hecke algebra, and using essentially those operators, we can reproduce an operator form of the an operator form of the Kassaman-Shalaika formula, and with slightly modifying these operators, we can recover the spherical function as well. Okay. And again, I won't prove these, but I will just say that much of this story is understood through the action of the Iwahori-Hecke algebra, or indeed the spherical Hecke algebra, and C lambda check, and the Iwahori-Hecke algebra having commuting actions on some sort of bimodule. This bimodule consists of the Iwahori, or indeed in the case of the spherical Hecke algebra, the k fixed points of the universal principal series representation. So I'll just write this here in case you're somewhat familiar with this object, but if you're not, then don't worry about it. The point is there's a bimodule, and understanding and analyzing the action of these two algebras on this bimodule gives us a lot of the story. And this is related again to the universal principal series. Well, this is the I fixed points of the universal principal series representation of the group G. And then what sort of techniques do we employ in proving these things? Well, something that we often do is reduce to rank 2. So what that means is that we have embeddings of SL2 into our group G, so SL2QP into our group G, and instead of understanding what the whole group does, we understand what an SL2 subgroup does in it. One thing that I've mentioned before is the Bruja decomposition of G. Well, this is writing G as a union of Borel double cosets. So remember, in SLRQP, the B is just the upper triangular matrices. Well, that's one instance of a Borel anyway. And G can be written as a union of double cosets indexed by the while group. And something else one might use is the Bruja-Titz theory of buildings. buildings, sort of starting from the cartan of the Lie algebra of G, dividing that with hyperplanes into some geometric configuration and understanding how the group acts on this geometric configuration. And I mean, of course, everywhere here we are computing integrals. According to a Haar measure. So sometimes nothing else will do. We will just have to compute a p-adic integral. Okay, and I mean, of course, what is interesting to us is what will happen to these techniques in the infinite dimensional setting. So some of these will fall apart completely, and then some will have to be replaced by some stronger versions. And I'm sorry, I can't resist, but say that metaplectic versions of these formulas exist. So in what I mean is that here we've worked with an algebraic group effectively, but if we take an extension of this algebraic group G by a group of nth roots of unity, and we consider this metaplectic group, then sort of there is an analogous story. And if one is interested in, for example, metaplectic Eisenstein series and their coefficients, multiple Dirichlet series, then their p parts can be studied, for example, by a metaplectic Kassaman-Shalaika formula locally. Okay. Okay, so what happens in the infinite dimensional setting? What goes wrong? So far, what we've done, right, is we've started with a familiar group G, and to it we have assigned a root system, phi, a Weil group, a co-weight lattice, ultimately a lot of combinatorial data that can be captured by a Cartan matrix. But of course, I mean, if we start with this combinatorial data, G, the group, can be recovered. So, for example, we can given a Cartan matrix, we can construct a Lie algebra via the Chevalier presentation, and then similarly, we can recover the group G via the Steinberg presentation. So we can generate G using some basically by finding these SL2 subgroups inside of it. Now, if we start now instead with a generalized Cartan matrix, then we can carry out steps similar to this and build a Kac-Moody group by constructing a group functor that gives us a group in this way. So we can, starting with a generalized Cartan matrix, we can build a group functor G, which gives a group little g when we plug a field into it, sort of similarly to above. Well, I mean, this similarly is doing a lot of heavy lifting. Really, what I mean is that there is a Tietz functor, which is a somewhat subtle construction doing this. So these constructions, there are similar constructions explained by Tietz, Mathieu, Carbone, Garland. etc.
Sorry,
Okay.
Anna, I have a quick
Yes.
question. When you
Yes.
recover G from the Cartan matrix, are you assuming simply connectedness or something else?
Sometimes. So, for example, I mean, I should say that when I say we recover G, I mean, if really technically, if I'm doing this Cut-Smoothie construction, I won't recover all of my favorite reductive groups. Like, for example, I won't get GLR. And then later on, so for the general Cut-Smoothie groups in the results, I'm going to say some of them require simply connectedness and others don't necessarily. So not all of the Cut-Smoothie groups are simply connected in some appropriate sense, but sometimes I will need them to be for the results I cite. Okay.
So in
And so,
particular, if you start with the simplest Cartan matrix, which is just 2, you'd get SLR, not GLR or
yes,
GLR. Okay,
yes,
thank
I
you.
believe you get SLR there. Yeah. Yes. So again, I mean, this is again as we, I mean, along the way, right? When we construct this G with the Steinberg presentation, along the way we have the Chevalier presentation of a Lie algebra, and similarly here we get a Cut-Smoothie algebra along the way, and the resulting algebra and group may be well, it might be of finite type. Oops. Which again recovers reductive groups. Well, I should say types of reductive groups. Meaning for each Cartan type, I get at least one, but maybe not all of the ones I like. It might be of affine type, which again recovers loop groups associated to finite dimensional groups. Or it, well, might be something else, which I will refer to as general Cut-Smoothie type. Okay. And then, well, what do we do with this? In order to try and understand the story, some of the story that I've outlined in the finite dimensional setting, there are sort of two approaches that we can take. So one approach is to um, use analogs of the finite dimensional decomposition theorems, so the Bruha and Iwasawa coming from the sort of this Tietz construction and the Tietz system to understand the subgroups and the structure of G. So maybe what I will say is kind of prove analogs of Bruha decomposition, etc., sort of analyze the Bruha-Tietz system underlying the construction um, to um, to prove facts about the or study the structure of the group. And the other approach, so this is roughly the approach in papers I'm about to mention by people like Braverman, Garland, Kashdan, Patnaik, Ali, etc. And then the other approach is to find G inside the automorphism group of a geometric object. So find G inside the automorphism group of a so-called mazur A Mazur is a geometric system that generalizes the Bruhatitz building of a reductive group. And this is the approach taken in papers by Nicole Bardipans, Stéphane Gosson, Guy Rousseau, Charignon, Hébert, Abdelatif, etc. Okay, and then well, these approaches lead to some results. But before I say something about the results, I wanted to say a little bit about the difficulties one encounters. I mean, there are some immediate difficulties that are maybe sort of obvious. The root system is infinite. The while group is infinite. So now a sum over the while group will be immediately more poorly behaved, and the product over positive roots will have some sort of convergence issues that we have to worry about. And well, if you've ever tried to do anything in this area, you might remember using the longest element of the while group. Well, now there's no longest element of the while group, which in itself is cause for chagrin. Furthermore, an interesting fact is that the coate lattice is no longer equal to the while orbit of the dominant part of the coate lattice. So it no longer made up of W translates of the dominant weights. So a new object appears, the Tietz cone, which is instead the union of W translates of dominant co-weights, and this will play a role. And then some bigger ticket items fail as well. So for example, remember I mentioned the Cartan decomposition, writing G as the union of double cosets indexed by dominant weights. Well, this is no longer true. Now there is instead a semigroup G plus within G, which consists exactly of the elements where the Cartan decomposition holds. But here the double cosets are indexed by the Tietz cone. So that's one way where this Tietz cone plays a role. And this is, well, the non-trivial fact is I can take this and it is a semigroup. And I just want to say that the definition of the subgroup K here depends, at least a priori, on the approach chosen above. So we may either think of as the Tietz functor on the ring of integers, or the stabilizer of a point in a Mazur. And there are cases where these two are known to be identical, for example, in the untwisted affine case, but in general, this is a bit of a sticky issue. And then another thing that is a big problem is the lack of a Haar measure. So, in the finite dimensional setting, we were working with a locally compact group that had a Haar measure on it. And whenever we wanted to define our favorite algebra, we just took an integral with respect to that Haar measure to define a convolution product. Now, this convolution product doesn't make any sense anymore. So instead, we have to replace it by some sort of formal convolution. So when we want to define an algebra on let's say Iwahori double cosets of G plus, the multiplication will have to be defined as a formal product, and the coefficients on these formal product will be, well, somehow be recovered by analyzing where the elements of a product of two, elements from two double cosets lay. And in order to make sense of a convolution product like this, one needs finiteness results. So for example, we will need that the product of two Iwahori double cosets, where the indexing element is in the Tietz cone, the product of two cosets lies in the union of finitely many cosets, so that we can define this convolution product over some as a finite sum. And then we need some further technical conditions of some intersections of double cosets being finite. So quite a lot of work goes into defining the algebras that we basically got for free from the Haar measure before. Okay, but one can do this, and there's lots and lots of results, which I will attempt to overview now. So here are some results and some sources in the infinite dimensional setting, by which I mean some papers that I mentioned, which are good sources of information. And of course, the remark is that this is a very, very incomplete list. There are many more papers written on this topic, some of which I will mention. And there's also some assumptions that I'll try and say. So, for example, the spherical Hecke algebra was defined, and the Satake version of the Satake is isomorphism proved in the affine setting by Braverman and Kazhdan in a 2011 Annals paper. And then this was in the, again, just for affine Kac-Moody groups, basically loop groups. And I think they needed, for example, a simply connectedness assumption, though the paper has a comment that they believe this is not necessary, but they somehow can't do without it in the way they wrote the paper. But the general sort of Kac-Moody version via the Mazur approach was done by Gosson and Rousseau in, again, an Annals paper in 2014. And then via the Satake isomorphism, one can then ask how to express Macdonald's spherical function. This was done by Braverman, Kazhdan, and Patnaik in 2016. This is for untwisted affine Kac-Moody groups in simply laced types. And in more generality, for, I think, almost split Kac-Moody groups by Bardi-Pons, Gosson, and Rousseau in two different papers. And then an affine, so a loop group analog of the Kassaman-Shalaika formula was proved by Manish Patnaik in the affine setting. And then in joint work, we proved a metaplectic analog of the Kassaman-Shalaika formula that works in Kac-Moody generality, and I suppose one can then specialize to the non-metaplectic setting in Kac-Moody generality, though I will say that the resulting formula is more precise in the affine setting in a sense that I will explain in a moment. Okay, so there's a lot of work that goes into, and a lot of, as you can see, fairly recent work that goes into just defining a lot of these object algebras and proving analogs of these classical formulas in Kac-Moody, in the Kac-Moody setting. There's sort of further work by, for example, Auguste Hébert on representations in the Kac-Moody generality, or sort of a limit of the Macdonald spherical function, the Gindikin-Karpelevich formula, was proved by various people in various levels of generality with these two approaches. So, for example, by Braverman, Garland, Kashdan, and Patnaik in the affine setting. Then by Auguste Hébert in Kac-Moody generality using Mazurs, and then by Abid Ali by Kac-Moody generality, not using Mazurs, but perhaps using a slightly different group functor. Okay. And then, okay, so just, sorry, a list of comments. I'm fast running out of time. So let me just make a couple of comments on and mention some features of these results. So one thing I've already mentioned is that the subgroup K, so the analog of the maximal compact, is a priori not identical in the two approaches. So these two groups of papers work with a K that is at least seemingly different. In some cases, it is not actually different, but this has not been completely satisfactorily explored. The formulas, so both the Macdonald's formula for the spherical function, the Kassaman-Shalaika formula, but basically many other formulas that, so anytime one wants to extend the formula from the representation theory, from the finite dimensional setting to the Kac-Moody setting, there's a new feature that they all share, which is there's a correction factor. This correction factor is related to Macdonald's constant term, and in fact, the exact value of it is understood by Cherednik's solution to the Macdonald's constant term conjecture. Basically, the way it appears is I've mentioned that these formulas can be written in terms of Weil symmetrizers or Hecke symmetrizers in these operator form, and understanding the relationship between the Weil and the Hecke symmetrizers, there's sort of a factor of this correction factor, which is trivial in the finite dimensional setting, but not in general. And here are some papers on this. Our joint work with Dinakar Muthai and Ian Whitehead sort of shows how this is a deformation of imaginary root multiplicities, and we show some identities about it, and then Janse Chen analyzed this analytically. Some sort of other comments. So the Sataka isomorphism, I mean, before we were talking about polynomials, now, so elements of C lambda check. In the infinite dimensional setting, we need a completion of this, of course. So, I mean, convergence issues abound. And another thing I wanted to mention is that before the double coset basis of the Iwahori-Hecke algebra was indexed by an affine Weil group. So the semi-direct product of the Weil group and the co-weight lattice. So now in this double affine setting, we get a basis indexed by the Weil group semi-direct product, the Tietz cone. This is not a group, so certainly not a Coxeter group, but interestingly, it has some similar features to a Coxeter group. So it has a Bruja order, and there's a corresponding length function. And in fact, the Iwahori coset basis, while it doesn't have an Iwahori Matsumoto presentation, it does have some Iwahori Matsumoto type relations, and it displays some strangely Coxeter-like behavior, which you can read about in this paper. Okay, I think that's all I wanted to say, so I will stop now. Sorry for going for very long.
Thanks for the great talk. Are there any questions or comments from the audience?
To consider representation theory of these affine groups, loop groups, something like that, in terms of generalization of Brattich building.
Yes, so I think sorry, did you say in terms of the building?
So generalization of building. What was the name? I forgot the name.
The Mazur, yes. So actually, this is I should have mentioned this. So these mazurs that are the analog of the Bruhatitz building, previously they were called hovels. My understanding is that a mazur is just a French word for a hovel, so it's sort of an outbuilding. But for example, in the 2014 Annals paper, it is still called a hovel. And I think Auguste Hébert has some papers on this. Has some papers on the sort of analogs of principal series representations, and he works with mazur, so it is in terms of in the mazur language.
Does it also involve certain generalization of paraholic groups?
Yes, I think there is something like that too. I don't really know the details there though, fortunately.
So,
Yeah.
what is the first paper to introduce Mazur? Is-
Oh, I think
I have
that
not
those
heard
are,
about.
sorry.
I have not heard about that actually.
Oh, so I think those are papers by Rousseau and maybe Charignon. So Mazur's sort of originally, I hope I am not lying with this, but certainly a lot of paper, a lot of references, sort of fundamental references were written, even if maybe I'm not 100% sure the first ones, by Rousseau and also papers of Charignon. So it will be called something like mazurs associated to a Kac-Moody group or something like that. Maybe I won't write maybe the words are
Okay, okay. Thanks a lot. I will search it.
um, but uh, but they will be in French, I think. Yes. I think the all of these papers are referenced in the bibliography of this paper. All the ones I'm thinking of anyway. So this one has references some, I think, 2011 papers by Rousseau that explore this very carefully.
Thank you.
You're welcome.
Any other questions or comments? So I have a question. When you construct the Ivahori-Hecke algebra for a Kac-Moody group, are there any connections? So you can think of the Ivahori-Hecke algebra as some affine version of let's say finite-Hecke algebra in the classical case. When you consider the Ivahori-Hecke algebra of a Kac-Moody group or loop group, are there any connections with the double affine Hecke algebra of Cherednik?
Oh, yes, and thank you for asking this because I meant to say this. So yes, there are. So I think, I mean, there's sort of many closely related algebras here, but I think maybe the thing that's true is that uh, the BKP algebra introduced in this paper is somehow analogous to Cherednik's Daha at the positive level. So it's maybe not quite the same algebra, although I think in some of the Bardi-Pans-Gosson Rousseau papers, the algebras are claimed to be just the same as Cherednik's Daha. Um, in 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 the um, in the BKP paper, I think there's a sort of a careful explanation of this. There's also this Gelfand-Graev algebra that one can talk about, which is slightly larger. That's not the Wahori-Hecke algebra, but it sort of combinatorially makes a lot of sense, just building it from the Lie algebra, so I think somehow the issue with the Daha is that we have the Tietz cone and not the complete co-weight lattice. I think that's what makes it not the Daha exactly, but it's close, I think.
I see. So the difference would be the Tietz cone versus everything else.
I think so, yes.
Okay.
So
Okay.
the Tietz cone somehow, I mean, there's many equivalent descriptions of what the Tietz cone is. Sort of the elements of lambda check that are that pair positively with all but finitely many positive roots, for example. And so these are somehow elements of a positive level. If you kind of interpret it in the loop algebra setting, these are the sort of positive level elements, and that's why there's somehow, I think it's bigger, or sorry, smaller than the Daha as a result. But I should never venture to try and make a statement with one bit of information, because I'm sure to be wrong. But I think
in
smaller.
particular, this would give you versions of Cherednik's Daha for general Kac-Moody group, right? So I think Cherednik originally
Yes.
introduced Daha just for maybe loop. I mean, yes, something like loop groups, but not Kac-Moody groups. So this would be some kind of version that appears, right?
Yes, and so for example, that's one of the difficulties in thinking about this correction factor that appears, is that kind of understanding this correction factor in the affine case is sort of done by Cherednik's result, and kind of when you expand it over some lattice, the kind of non-negativity of the coefficients is understood well in terms of the kind of an affine root system. But in the Kac-Moody generality, there's still some non-negativity, but suddenly you don't know kind of what that counts. And so there's kind of some mysterious questions that I'd love to see an answer for there. Like, you know, for example, imaginary root multiplicities in the affine setting are easy. They're all just one, they're all the same. They're all the rank or the rank minus one maybe. But in the general Kac-Moody case, there's no sort of well understood closed formula for them, but they are somehow contained in this correction factor, in a trivial way, I guess. But
I see.
yeah. But the picture is a lot more subtle somehow.
Okay, thank you. Are there any other questions or comments? All right, so thank you everyone for showing up. This is the
Thank you very
last
much.
talk of the last colloquium talk of the semester, and I'll see you next semester, I hope. Have a good summer break.
Have a nice
Let's
summer
thank our
break.
speaker again.